All right, Jeff, good to meet you.
Yeah, all good. Good to have a chat.
I know Jeffrey from a bunch of TikTok lives. He is on and he's always super well spoken. I think you were on Globebusters years ago. Is that true? Do I remember that or no?
No,
Okay.
I'm fairly new, probably about 6 months that I've been on TikTok panels. For some reason, just felt compelled to go straight up. So I'm probably flat earther from about 8 months ago.
Oh wow,
Uh,
you're
yeah, I
real.
went straight onto panels. I went straight onto panels and then went pretty hard from there and just gained some knowledge and became a sponge. So I just absorb anything that I can from anyone and then try and round it out.
What is your
So,
background? Can I ask?
yeah, so ex-military and I'm a personal trainer, nurse, so bit of a mixed bag. I've also done missionary service, so I have a very sound knowledge of Christianity and religion through history. Uh, yeah, a bit eclectic, I suppose.
All right, and when Jeffrey's on a panel and he's given the leeway, he will talk high level, very intense, to the
Mm.
detail. I'm going to ask you to just keep it super simple for this
Uh,
conversation. All right.
that's hard. That's hard for me.
I know it's hard, but I'll reel you in when necessary. The other day,
Okay.
you were on a panel and you were talking about the problem of the three body problem. And
Yeah, I like to do it in great detail.
let's do that. But again, we're going
Yeah.
to try to dumb it down for the people that are brand new to that never even considered what gravity is. Right. So go ahead, you go and we'll talk.
I'll, yeah. All right. So, I mean, the whole idea is that there's a preamble. You have to understand what the three body problem is relative to. So, there's a preamble that has to be established. So, the first part of that would be um, what is an orbit? An orbit is meant to be, and this is the definition that is generally given when you look up, an artificial intelligence response. It's a precise balance between inertia and gravity. So back in 1666, obviously in early 16th century, we had Copernicus putting forward the idea of why heavenly bodies moved, or how they moved, I should say. And then in 1666, Newton put forward the idea of what force creates that movement, and that was gravity. But we get then 1927, you've got a man by the name of Georges Lemaitre who put forward the idea of the Big Bang, and that creates the inertia. So an orbit is a precise balance between inertia and gravity. You need that exponential speed on the x-axis, which encounters the y-axis gravitational force of a body of larger mass. So you always go around a larger body, and these orbits tend to get faster and faster. So you kind of have to set that up. And so when we consider that you have that precise balance, what will happen is if your inertia is slightly too potent, that will eject the body from orbit and become like a rogue planet, for instance. When conversely, your gravity is slightly too potent, that body will be pulled in and make contact. So you either get ejection or collision. All right, if you don't maintain that supposed precise balance. I mean, elliptical orbits are highly problematic because that's not a precise balance. You're going in and out, right? I'm not going to go into that now, but so we've established what it is. It's a precise balance between inertia and gravity. The other thing is that Einstein said there is no static anchor. So gravity is want to hold things together, but it's also want to make things move. Right? So there's no static anchor. It's all relative motion. So if something looks like it's not moving, it's only because it's going slower relative to those things that are around it. So um, no static anchor. And then basically, if the universe is about 96% nothing, which in essence it is, so it's space. Space is nothing in essence. I'm not going to go into the newer, kind of
Mhm.
adaptations of dark matter and dark energy and quantum fields, which are meant to be the building blocks, blah, blah, blah. But in essence, space was always seen as nothing. Um, and the reason why it's seen as nothing is that if it is a something, if it's an atmosphere, that would create orbital degradation. And the whole underpinning of the global paradigm is that things go around other things in crazy fast, right? That everything's in orbit. So there is no static anchor in the universe, and there is no net zero gravity. So they tell you that the outer gravitational field of the Earth, for instance, is 4.5 billion light years. And I'm sure you know that a light year is 5.88 trillion miles. So take 5.88 trillion and times that by 4.5 billion.
Wait a minute. They say that the gravitational reach of the Earth is that far?
Yeah, the
So
outer
that
limit, 4.5 billion. So if the background's nothing, that nothing doesn't hold things together, right? Nothing's not a glue. So the glue is said to be gravity. And for that gravity to work, where it's surrounded by, say, 96% nothing, it's got to be pretty potent to hold everything together, right? And so that potency is expressed over insane distances. So once again, it's a precise balance between inertia and gravity. Number two, Einstein said there's no static anchor. Everything's in relative motion. Nothing is really standing still. You do have Lagrange points, which are kind of an exception, but only partially. And then number three is that there's no net zero gravity. Because if you have net zero gravity, there's no glue, right? If it's 96% nothing, nothing is not a glue. Gravity is the glue. So we've set that up. We've now set our preamble. So our preamble is basically everything is going around a body of slightly bigger size, faster and faster and faster. All right.
shouldn't we all
So
die when there's a planetary alignment? I
yeah,
mean,
well,
if
that's what I'm about to get into. So the three-body problem actually has three problems, and the first one is relative motion. The second one is proximity, and the third one is obstruction. All right. So this is why it's not only chaotic; it cannot be fixed. It cannot be solved. You cannot overcome it. It has no real essence to it. So the first one is relative motion. So let's say that you and I, Dave, are walking along a track, an athletics track, and let's say someone else like Gene, who was going to be here, is in the middle of that track on the grass. And let's say that you're the moon, I'm the earth, and Gene's the sun. And you want to get past me, you need to go faster than me, right? So the motion of the moon, or the absolute speed of the moon, is said to be 2,288 miles per hour. But the speed of the Earth is 66,600 miles per hour, which is exponentially faster than 2,288. So if you want to overtake me, then you better go pretty quick, right? You're actually going faster than 66,600. So if you're chasing a moving target, your speed has to be relative to that moving target. So as you come and you want to get past me, you would have to go my speed plus a little more. And as you get in front of me, I'm exponentially speeding towards you at 66,600 miles per hour. So you better get the heck out of my way, right? And so you're going to have to move even faster to get out of the way of me coming directly towards you at some serious speed. So if your speed's only, as the moon, is 2,288 and mine is 66,600 and you're going around me and I'm going around the sun, you're now chasing a moving target. So your speed has to be relative to that moving target, which means I can't give you an absolute speed, right? You have to slow down, speed up.
I tell people an example would be to have a car or a bicycle or somebody just moving down the road and then try to circle them in perfect circles while they're moving, right? You got to slow down. You got to maintain. You got to speed up. You got to slow down and speed. And it's like, what causes that? Is there a heliocentric explanation for why how the moon does that?
We're not even getting into orbits. So orbits, we have angular momentum or angular velocity, and that's acceleration by definition. And they go faster and faster. So, the Earth's going around the sun at 66,600 miles per hour. The sun, the Earth is then spiral vortexing with the other planets around the sun, around an arm of the Milky Way at 514,000 miles per hour. And then the entirety of the Milky Way is going around the inside of the CMBR at 1.3 million miles per hour. So if you're going to tell me that because that acceleration of 66,600 miles per hour is not particularly substantial, you're not going to feel it. I'm going to feel it by the time I get to the other end, and I'm doing 1.3 million, and we're supposedly doing an orbit with the galaxy that's, my goodness, it's meant to be 250 million years, Earth years, and 600 trillion miles. But to get back, the first problem is relative motion. The next problem is proximity. So let's say we've got the moon going around the Earth, as I said, that's fine. That's easy to factor. But now, as I said, as Einstein said, there's no static anchor. So that Earth now has to move relative to something else, and they say that's the sun. And so the moon is going around the Earth at 2,288. The Earth is now going around the sun at 66,600. And let's say that we know that the given distance to the moon is 238,000 miles.
What they claim.
And so if I have the moon, then the sun, then, the moon, then the Earth, then the sun, and then I rotate 180 degrees so that I have now the moon's done half of its orbit. It's now the Earth, moon, sun. That moon is closer to the sun, closer in proximity by 500,000 miles approximately, right?
Right.
So as it gets closer to the sun, which is said to be 1.3 million times more voluminous than the Earth, massively bigger, the big boy wins in a tug of war. So as it gets closer to that and increases its proximity, some of that energy, that force is going to be exerted upon the moon more substantially so because of 500,000 miles of increased proximity. And so if that happens, as I said before, we have to have a precise balance of inertia and gravity. Otherwise, we get ejection or collision. You're going to get ejection or collision. You're going to. And you might say that it's only a small force, but it keeps doing that. And so every time it gets closer, it's going to eat away at that precise balance of inertia and gravity, and you're going to get chaos. So that's proximity. Then you have obstruction. So if as I said, it's 96% nothing. The glue is from the 4%, the bodies, the Earth, the sun, the stars. That glue has to express itself over nothingness, over a distance. So if I have that force, that energy over distance through nothingness, and the moon gets in the way, it's now obstructing some of that gravitational force that should be expressed upon the Earth from the sun. And so once again, it's in the way of the expression of that energy over distance. And so that is also going to create orbital degradation because it's going to disturb the precise balance between inertia and gravity. And so at the start, we have relative motion. We then have proximity, which is constantly changing. Like I said, the moon can get up to almost 500,000 miles closer, generally speaking, to the sun. So that proximity is going to degrade those orbital mechanics as well. And last but not least, the obstruction from one body to the next is going to stop the effect of that energy being expressed over distance. So it is inherently insane and chaotic. It can't be fixed. It cannot be solved.
When you were arguing or trying to explain to a Globe zealot, and their only argument was, "Oh, you think there's only 3 bodies in our solar system?" Do you remember that?
Yeah, and that creates a significantly more complex.
Yeah, well, like the 2 bodies is not a problem. 3 bodies is a problem. 4 bodies is a massive, bigger problem. 5 bodies, saying that it's exponentially worse doesn't even describe how much worse it is. So,
well, that's the thing too. If everything's in relative motion, and your paradigm is basically that things go around slightly bigger things insanely fast, where does that end? There's no static anchor, right?
Right, and then
if there's no static anchor,
how about
everything's
this?
going around something else.
Right. If we drop something in the atmosphere, it'll reach a maximum speed because of wind pressure, and it might even slow down a little bit as it gets into thicker air. I don't think it's going to burn up. I don't have any proof that anything burns up when it falls down. I have proof that things don't burn up. But in space, an orbit is not anti-gravity. It's just we're falling at the same rate as the Earth curve. And there's
Yep.
no air resistance. So if we're falling, how come we're not speeding up? How come
Yeah.
satellites are not speeding up?
So and that's it. Look, there's often the misnomer that we're floating in space. You're not floating in space, because floating is where you have um, a rarer medium sitting atop a denser medium. Well, there's no medium, so you are falling. It's an orbit is also referred to as perpetual fall, because it's falling around something with that speed.
But it has to,
Um,
a satellite at whatever altitude has to maintain that speed to maintain that orbit in theory. But if it's falling due to gravity, it doesn't matter if it's moving forward or falling straight down. It's the same thing in space. It would
yeah,
always be speeding up. And then that perpetual balance is gone in a split second.
yeah. So they say that there is no directional bias in space. Basically, falling is relative to the next body of greater mass. All right. And that's why they also have to say that there's no net zero gravity, because otherwise
Yeah.
you'd actually be falling, right? You
And
know what I'm saying? It's got to be
right,
glue.
right. What about, when you're talking about the orbit of the moon, and now how far did you say the Earth's gravity goes?
So they say basically they talk about gravity being in some way infinite, which is ludicrous. But references that I got said the outer limit is 4.5 billion light years,
4.5.
which is
Wait, hold on. 4.5
billion,
light years or billion light years?
billion light years.
That's stupid.
And,
I
and
mean, 4.5 light years is stupid, right?
yeah,
4.5.
well, then you get the idea that if the glue is gravity and you have the concept of expansion, the expansion destroys
Wait,
the glue.
let's just put this into reference for people.
Insane.
4.5 light years. Forget the billion. Okay.
Yeah.
4.5 billion light year. 4.5 light years is where they say the closest star to our solar system is. 4.5 light years. That's 25 trillion miles, rounding off. 25 trillion miles. If you and I were in a spaceship going a mile per second, it would take 31,000 years to go 1/25th of the way there. And they want to say
Yeah.
that our gravity's still holding on, right? Globe.
Yeah. Well, this is the thing. Gravity seems to be potently impotence locally, but then it becomes,
I'm just blown away. I can't even believe that they claim that. What you just told me is absolutely blowing my mind. So, would Jupiter have even a farther reach than us because it has so much more gravity? Would the sun have a farther reach, or, I mean, 4.5 billion light
light years.
years? That's the Earth.
5.88 trillion miles.
Yeah.
So 5.88 trillion miles times
And people
4.5
have no
billion.
idea even what a trillion is. So the sun, everything that has gravity is going to travel that far, if not farther. If it has more gravity, it would go even farther, right? More gravity, more
It's
distance.
1.3 billion times the mass of the Earth.
So it's 4.5 billion light years times 1.3 million. That's how far the sun's gravity goes.
Well, the sun is 1.3 million times more voluminous than the Earth. It's massive comparative in their paradigm. For you and I, we believe it's local and that it's a load of garbage. But anyway.
So,
yeah.
So again, just looking at anybody that thinks this through has to just throw out the heliocentric model. That's the problem. The problem is people don't have the ability to think. They're fluoridated. They got the human pincushion. They're unable to think. They're indoctrinated from their Rockefeller textbooks. When a couple months ago, they said, all the planets were lining up. Well, what about all that gravity? What about when the moon comes towards the sun? The gravity should speed it up a little bit. Then it has to kind of arc around because the Earth's gravity is going to hold it. It's not going to get ripped away. Why wouldn't the moon just go around towards the sun? And then it has to go away, and the sun's gravity would be pulling on it.
And as you had that moon in front of it, the moon can't move 2,288 miles per hour because the Earth is moving 66,600 miles per hour, and it's careening towards it as it comes in front of it. It's going bang, it's going to hit it.
Well,
It
no,
needs to
it
get its
speeds
butt
up.
out of the
You don't
way.
understand. The moon's going 67,000 miles an hour, and here it's going 68, 9,000 miles an hour.
Yeah.
Then it slows
Right.
down, and now it's going 66,000 miles an hour. And now it's speeding up to 67, and then it's going to speed up again.
And that's the carry on effect. It's like the butterfly effect. That's going to carry on along the chain. You
Right.
know, the idea of relative motion, of proximity, of obstruction. You know, you've got utter chaos along the chain. So basically, you're creating a paradigm that can't exist in the first instance. It can't exist.
Jeff,
And then at the other end, you can go into what's called the nth degree problem. So at the start, you can't model it, and at the end, it destroys itself. So if we are in a, you know, they go out to the CMBR, the cosmic microwave background radiation, which is the leftover kind of haze or radiation from 13.8 billion years ago when the Big Bang happened, right? So they factor
the
to that
Big
because they
Bang
say
that was
they can't.
made up by a Jesuit priest.
By Jesuit priest Georges Lemaitre,
Yeah.
in 1927, and so this is the idea. They can only see to that point, and they can't factor further. But if you agree with Einstein that there's no static anchor, and you agree that gravity wants to hold things together and wants to make things move along with inertia when they pair together, then in a potentially infinite universe, you have to continue to factor that because you can't be static. And so something is going around something slightly bigger because it has to have a greater gravitational field, right? Mass attracting mass kind of thing. So it has to go around something bigger and go faster and faster ad infinitum. We already go from the moon doing 2,288, you know, the Earth doing 66,600 miles per hour. Nice use of the mark of the beast. We then have, you know, us spiral vortexing with the sun around an arm in the Milky Way at 514,000 miles. And then at the other end, we have 1.3 million miles for the entirety of the Milky Way. Now, if you continue past that CMBR and you don't have a static point, and you have, you know, gravity being the glue, which wants to hold things together and move, then you're going up and up and up and up. So we could be theoretically doing 50 trillion miles per hour. And if you want to tell me that 66,600 miles per hour, you're not going to feel the acceleration due to angular momentum, right? Due to acceleration. You're going to feel it at 1.3 mil, and you're certainly going to feel it at 50 trill. Now, eventually, even though space is said to be nothing, and the reason they say that is because if it, as I said, if it had an atmosphere, that would create friction, and that friction would degrade orbits. That would destroy your balance again. So they have to declare that it's nothing. Interesting, Aristotle, who started this, right, the idea of the globe, not the heliocentric model, that was in the 1600s. But he put forward the idea that nature abhors a vacuum, hates it, and that if something moves in the heavenly bodies, it should move through a substance. And he called that the quintessence, which is the ether. NASA has the exact opposite paradigm. They say that nature loves a vacuum and, in fact, needs a vacuum because if something moves, it should move without friction, right? In nothing. And so they have the exact opposite paradigm. Now, and as I said, if you do that, that keeps going to the nth degree. And let's say you're doing 50 trillion miles per hour, right? Because all those speeds are still relative to the Earth because it's moving in with the galaxy, you know, yada, yada. Then everything would be torn apart. There would be no structural integrity once you get to a certain point. So you can't reason this ad infinitum. They say they can because there's no friction, there's no, you know, feeling or sensation of the speed because you're going through nothing. But the mere fact that you are going in an orbit is acceleration and is destructive. It's like when you're in an aeroplane and you're going, you know, straight and level, you're not going to feel it too much. Agreed. You're in an enclosed system. But if that thing starts to bank, you're going to feel that, right?
As soon as the pilot starts to descend, you wake up. You're like, "Whoa! I changed vectors." You know
exactly.
it. You know it immediately. All right, I want to kind of keep this a little short, but I want to touch two more things on gravity.
Yeah.
Would centrifugal force be the same as gravity? I mean, the force. Like, because it might be a stupid question, but somebody brought this up, and maybe you were on the live when they did this. They said an experiment whether gases are attracted to gravity is have a bucket of gas, and you know you can swing a bucket of water around and put it in a centrifuge, super fast and then suck the air out of that room. Would the air stay in the bucket due to the centrifugal force? I know a rock would stay in the bottom of that bucket, right? All right, so that's something just to think about. The other thing is,
and the thing is that water would it wouldn't be concave; it would convex. That's what we see when we have that kind of effect. So it's the exact opposite of what they're saying.
The water would
climb up the walls of the bucket.
Yeah, no, that's if the bucket was spinning. But if the bottom of the bucket was to the outside, it would be pushed to the bottom of the bucket. And I think it would. I think it would take the shape of the bottom of the bucket. I'm not sure.
As it pushes out, it's also going to, because of the, once you get to a certain speed, it's going to come up the side as well. You're going to get concavity rather than convexity. Right?
Yeah. It's going to be concavity to the circumference of the circle that you're making. It's gonna match that. All right. So Globers say, you can't feel the spin of the Earth because it's only going around once a day, half the speed of an hour hand on a clock, which is stupid. Because my analogy is, if you're on a merry-go-round that was regular size, merry-go-round that was spinning once per day, you'd barely notice you were moving if you'd notice at all, right? But expand that out to 24 miles in circumference. Now you're moving a mile an hour. All right. There's really not much centrifugal force there, but now make it 24,000 miles around, right? Now you're going 1,000 miles an hour, banking to the right at 60 miles an hour. You're going to fly off that horse.
Yeah, you represent that angular momentum as tangential velocity,
right?
And you're going stupidly fast.
And to prove, and I've watched somebody spinning objects up, and objects when they wider objects as they spin, they explode. But when the smaller objects don't explode at the same RPMs, right? So,
well, as far as the merry-go-round analogy, that definitely, they say you're rotating once. But if you've got that exponential distance, obviously the man in the middle is barely moving at all. But the man on the outside of 24,901 is moving over a massive distance at massive speed.
If the guy on the inside horse that's just we'll say a mile from the center of the merry-go-round, he's moving at less than a mile per hour, like super slow. He's not even. But the guy on the outside is going. It's like you're on the top of an airplane that's banking to the right and going twice the speed of a normal airplane.
Yep.
The point I wanted to make is a simple experiment that anyone can do is. I gotta film this because I did it years ago and I didn't film it. Get a rock and put it on a little string, maybe 6 inches, and just turn around. Just a regular spin around, and the rock will barely lean outwards due to the centrifugal force, right?
Yeah.
So then get a rock and start spinning around and let that line out farther and farther and farther. And you'll notice the farther out you go, the slower you can spin, and the rock will maintain, would not hit the ground. The object you have. So you can, as it gets farther and farther out, you can go slower and slower and slower.
Yeah.
And
that's the trouble. It's the idea of physics, isn't it? It takes more energy to initiate movement than it does to sustain movement. That's fascinating physics. Yeah,
Jeff, that's what I wanted to talk about. I'm going to keep this short. I'm going to put this in the gravity section on the app and upload it on my channel. And
when the person is ready to have the session, you will look for the resonance point in each one. So you turn on the machine, adjust the distance of the spar gap, and with one hand, the one that is connected, the accessory, and another, the tuning, you will look to the resonance, moving all the coil up and down slowly, and with the hand that is connected to the accessory, you need to listen and feel where you are getting more energy, and that will be where is. Listen to the sound, one hand in the wire of the accessory and the other in the tuning, moving all the coils, and when you find where is more sensation of energy in the accessory wire, you will find the resonance. And remember, the person must be connected and the feet must be raised from floor.